Hello, my name is Kyle, and today I'll be presenting Liveness Aware Memory Allocation for HoneyPotion. Let's get started. So, for those who are not acquainted yet, HoneyPotion is a framework that brings the power of eBPF to Elixir, allowing users to write Elixir code that is transformed into eBPF bytecode. So, whenever we are doing memory alloc, we have to keep in mind that Elixir has immutable and dynamically typed variables and is functional, while eBPF has immutable and statically typed variables and is imperative, similar to C. Our old solution would take new Elixir variables and represent them in the C version 1-to-1. Also, almost every expression would be evaluated to a helper variable, and then would be passed on to its final usage. So that gives us some troubles, given that eBPF programs run in the Linux kernel inside of a sandbox. To avoid problems with the system and follow safety constraints, eBPF limits its stack size to 512 bytes. Also, eBPF does not give the user standard heap allocations through malloc. So this gives us trouble specifically with program size. With that limitation, we are limited by the number of variables. Here's an example of a benchmark that reaches our limit, and as you can see, it's not many lines of code. So we came up with a solution. Although the stack size is limited, we can take 3 steps to improve our situation. Reuse variable positions that are dead through liveness analysis, defragment for differently sized variables, and move the stack to an eBPF map. Let's go step by step how the solution was built. So first, liveness analysis. To define when variables are dead and can be replaced, we rely on liveness analysis. Elixir gives us access to the program's AST. As a result, we can solve liveness analysis with 2 passes through the code. One backwards to define the points where variables will have uses, and one forwards to check variables that are in scope. We can get dead variables by checking those that are in scope but do not have any more uses. And also, eBPF provides to its users eBPF maps, data structures that can keep large amounts of data. You can imagine this as if it was our heap. Currently, the stack is an eBPF map with 4096 bytes, declared similarly to a char stack of 4096, and is accessed with pointers for different types, such as integer pointer for stack int and so on for different types. There at the bottom you can see an image of how the eBPF map is declared. So, the stack is implemented both in C and Elixir. The bottom half is of Elixir and the top half is of C. So let's start with that. Whenever we want to allocate a variable, we first pick up the stack type variable that represents it, so it is the pointer to that type, and we typecast the position that we want in the stack to that type, so that now we are dealing with that specific type when we do operations. Finally, we dereference that position so that we can alter its value and equal it to the value that we wish. While the usage is much simpler, we simply dereference the typecasted pointer to the stack plus the position that we wish to use. But memory management in the Elixir side can be a bit complicated. After all, we have to keep the free blocks of memory that we are using, as you can see in the bottom images. So, first, those free blocks are represented by tuples of positions and sizes. To manipulate these, we have 2 functions, get and give. The get function picks up the context, which is where the memory blocks are kept, and the size that we want to get, and gives back a new version of the memory blocks or the free blocks without that position and the position that we have for the variable. And the give gives back when a variable is deallocated so that the memory management free blocks now has it in mind. Also, we have a map that points variables to their position and size so that we can translate it in the program or give it back. At the bottom, you can see that whenever we are declaring new variables, they can pick up different sizes, and we also can have gaps. So, sometimes when the stack gets full, we can run a defragmentation to remove empty spots and free up space for new elements. If after the fragmentation we still lack space, then our stack does not fit in the eBPF map that we defined, requiring bigger space. However, we can't defragment with standard branches in our program, as we could generate different stack states before eventual merges. So, we came up with tree split, where we pick up the original program, and whenever we were to do a merge, we instead duplicate the tree. As a result, the tree is splitted into different versions, and any sequence that you follow there, you can see is simply a sequence of instructions, without any merges. So, instead of being limited by 512 bytes, we are now limited by 4096 bytes of space that is being reused. Given that we are unlikely to have so many concurrent variables, our real limit is the eBPF instruction limit, which is 1 million instructions. Our benchmarks tend to stay in the 100. So, I believe we have come to a solution. Thank you very much for watching.